Hi everyone. The topic of this paper is very interesting. It is about a kind of deadlock immunity which name is immunix to defend against deadlocks. As we know that deadlock is a headache bug in multiple thread system. One of main targets in writing concurrent software is avoiding deadlocks. It is considered the most challenging endeavors because it requires carefully reasoning about complex interactions between concurrently running threads. Usually, when users encounter deadlocks, they need to ask help from developers and wait for an update patch to fix the software's bug. The authors of this article developed the Munix which can solve the problem automatically. Furthermore, the Munix can learn the bugs by itself and avoid the same crash in future running. Before introducing this approach, let us review some basic knowledge in the background. In what kind of situation does deadlocks happen? Multi-thread system. Multi-threading is the ability of a program or an operating system to enable more than one user at a time without requiring multiple copies of the program running on the computer. Multi-threading can also handle multiple requests from the same user. In simple words, multi-thread can make tasks running in different processors at the same time to speed up the running time. If there are several tasks running together, something wrong will happen when they access the shared data. A process reads the data and wants to modify it. B process needs the modified data by A, but B reads the data before A's modification. Then mistake happened, for B read the wrong data. To solve the problem, people involved the lock and unlock conception. It is very similar as the SQL database. When a user accesses data, other users cannot do the same thing until the user finishes his access. Lock is a synchronization technique used to limit access to a resource in an environment where there are many threads of execution. Unlock is to release the locked area. Then other processes can access the shared resource. Thus, the lock and unlock method create a new problem, deadlock. Deadlock is any situation in which no member of some group of entities can proceed because each waits for another member, including itself, to take action, such as sending a message or more commonly releasing a lock in concurrent computing. It is very common in multi-processing systems. Finding a deadlock and solving it is a kind of debugging in programming. However, it is a hard and low efficiency process. There are already many approaches to solve deadlocks, including either static or dynamic ones. They all have their own limitations. The authors introduced some main techniques in the articles. Language-level approaches use powerful type systems to simplify the writing of lock-based programs and avoid synchronization problems, but it is strict to developers and require them to adopt new languages. Transactional memory is simpler than language-level approaches. Transactional memory does not wipe out the cumbersome burden, but switches it from programs to the runtime. When programmers use large atomic blocks, all TM code calls into non-TM code. Its performance is still an issue. Time-triggered systems and statically scheduled real-time systems can guarantee safety and liveness. However, they need to know some parameters like mutual exclusion constraints and require processing time ahead of running. It is a huge limitation. The authors also talked about some dynamic approaches like model checker and RX. RX is a little similar to Damunix in that it can roll back a program to a checkpoint and retry it by modifying the environment. However, unlike Damunix, RX cannot learn how to deal with the same deadlock from the field experience. As illustrated above, the advantage of Damunix is that it can avoid encountering the same bugs. How does Damunix learn from fixed deadlocks? The main idea is that the program develops antibodies matching observed deadlock patterns, store them in a persistent history, and then alter future thread schedules in order to avoid executing patterns like the ones that were previously seen. With every new deadlock pattern encountered by the program, its resistance to deadlocks is improved. The structure of this approach can explain it clearly. As shown in the below picture, we can know that Damunix just built a deadlock basement which stores the signature of any occurred deadlocks. Every time a system meets a new deadlock, as React does, Damunix saves the signature of the starvation state and also restarts at a set of point. The advantage of Damunix is that it can match a new coming deadlock to its history library to avoid the same deadlock happening. It is a process of studying, so it cannot prevent deadlock fully. So I summarize the 4 steps as listed in the page. Meet a deadlock, matching it in exit storage. If it is a new one, store its signature in storage, then alter future thread. The specific process is more complex than the list. Let's talk the details. The authors talked about Damunix detail in these parts listed here, including some limitations. The code data structure is critical for the whole approach. They call it capturing synchronization. The authors use a resource allocation graph to represent it. RAG is a directed graph with 2 types of vertex, thread T and logs L, and 3 types of edges. Request edges indicate that a thread T wants to accurate log L. Allow edges indicate that thread T has been allowed by Munix to block waiting for L, and the hold edges indicate that T has accurated and presently holds lock L. It can be updated by the monitor. Another very important part is how to detect deadlocks and starvation. It is the monitor's job. The monitor thread will wake up in a certain circle time and update RAG by the events. It only searches the most recently processed batch of events as a universal mechanism for detecting deadlocks and starvation. As mentioned above, the monitor will save a yield circle's signature to the history. How to create the signature is also an indispensable part. In the paper, the authors use multi-site to store elements of a RAG circle, including all holds edges and yield edges. These signatures don't store program data. This character makes it more extensive. Next, the authors introduced how to avoid previously seen patterns. According to the paper, it is a part of monitor's code. The main idea is that the Munix intercepts all lock and unlock calls with a thread library. It uses the request method to judge whether allowing the current thread's lock request would make the program meet the same deadlock. At the same time, the authors need to adjust the suffix length of each call stack. This length of suffix is similar as a filter to the deadlocks. The holes of the filter are too large or small will affect the processing of the Munix. This is dependent on the false positive rate. The author also used several data structures to improve both symptotic and actual performance. They use a hash table to map raw call stacks to their own call stack objects. They use a version of Peterson's algorithm for mutual exclusion generalized to multi-threads and color-read DFS to find circles in the RAG. At the end of this part, the author also talked about the pros and cons of the Munix. It is also like the conclusion above. The Munix can help people dealing with deadlocks, but it cannot fix the code bugs. Sometimes it cannot avoid some extremely risky deadlock patterns. The Munix cannot induce a non-real-time program to produce wrong outputs. The authors have 3 implementations of the Munix, 1 for Java program and 2 for POSIX threads. In Java program, the Munix supports monitors and explicit locks. For POSIX threads, they modified the library in FreeBSD and the native POSIX thread library in Linux, which is part of glib. The evaluation is with several real systems as listed here, like MySQL, SQLite, JBoss, and so on. For all experiments in the paper, the author set the sleep interval as 100 microseconds. The measurements were obtained on 8-core computers, 4 GB RAM. The experiment's results are about these 4 parts: effectiveness against real deadlocks. The Munix almost correctly detected, saved, and avoided all patterns except in the case of ActiveMQ pattern 575. The authors also list some avoid deadlocks in Java JDK 1.6. Performance overhead. In real applications, it is reasonable to suggest that users encountering deadlocks be offered the option of using the Munix right way to cope, and they also observe that the Munix score well for up to 1024 threads. The thread implementation exhibits maximum 4.5% overhead, while the Java implementation maximum 17.5%. About false positive, they got the result related with suffix length. The bigger dips, the less positives. The final aspect of the Munix is how many additional resources it requires, compared to non-immunized programs. The result is insignificant. From all the experiments, the authors conclude that the Munix can develop resistance against real deadlock without any help from programmers or users. The Munix is suitable for large software systems with up to 1024 threads and keeps the correctness of general-purpose programs.